Good morning, everybody. This is Pavel Shamis from NVIDIA. We are kicking off our first session for Keynote, first Keynote for today. We are glad to have as our first presenter Robert Hormuth. Robert is Corporate Vice President at AMD. And he leads the strategy of the data center solution at AMD. Robert has over 35 years of computer industry experience. He joined AMD in 2020 after 13 years at Dell, and 8 years in Intel, and 11 years before this at National Instruments. At AMD, Robert in charge with creating long-term system-level vision for DG and identifying the technical requirements implication to the DG portfolio. Robert experience include I/O peripheral devices, x86 system design, BIOS, firmware, application software, FPGAs, ASIC. Robert holds a bachelor's degree in electrical engineering and computer engineering from University of Texas, Austin, and currently holds over 30 patents. Robert, the floor is yours.
All righty. Good morning. Can you hear me okay?
Yes, we can hear you great.
Okay. Well, good morning, good afternoon from everyone from around the world. Hope you're having a good day so far. Thanks for the opportunity to come speak this morning. What I'm going to cover is kind of the evolution of what we see happening on the Ethernet fabric space, and in particular, the impacts of HPC and AI. And I've got a special guest that's going to be joining, hopefully, midway through. I've got the chair of the newly formed Ultra Ethernet Consortium that's going to co-present from a UEC perspective on the formation and the principles of what's happening on the Ultra Ethernet front. So I'll be introducing the chair, Jay Metz, here in just a few moments. So my goal is to get out of the way and let Jay talk about the world of Ultra Ethernet and what we're aiming for, what the industry's aiming for there. So let me start with the obligatory legal statement of there could be some forward statements here. So please excuse that. Now, what we see as we map out the future, looking at where we need to go, as everybody knows, silicon design is a long process. It's a many-year process. We've all got to be visionaries and crystal ball readers and try and read where the puck is going. And when we look towards the future, we see kind of 6 big buckets of computing scenarios that are really going to be driving the landscape differently than they are today. The whole notion of deeper perception or intelligent everything, agriculture, equipment, production, real world simulation, about the more precise modeling and simulation of the real world, the environment, the oceans, weather, seismic, all of those things are being enabled and driving more demands. I think smarter and more inclusive AI. Surely everybody's heard of the buzz that is AI, but I think we're at the early dawn of AI still. I personally believe that, we're at the very early stages. We're moving from, the era of Big Brother to the era of Big Mother, i.e. human influence versus human assistance. And when we get into that human assistance era, it's really going to take off even further than it is today. All of that, it helps enable, better user experiences, interactions with technology, the virtual world. Data will be used by business to create new digital services that we haven't even contemplated. And sustainability, while not exactly a computing scenario, but it's so important to us that it's got to be at the forefront of what we think. Sustainability and efficiency is going to be massively critical on the success of technology in the future. And then this whole notion of subscription economy and institutional disaggregation. This is the notion of everything as a service. Changing traditional commerce barriers from B2B, B to me to you. All of those barriers are changing, and we don't know what the new one is. What's the next disruption like Uber or a Lyft or Airbnb or VRBO that's really breaking down some of those institutional barriers by disaggregating it. And then, the last piece driving us is the data sovereignty and security. Every country, region, state, city, village, regulations drive unique compute requirements. I get to say village here because I live north of Austin in Salado, and we're officially just a village, not a city. So those requirements or those foundations are shaping then, these 6 key technology inflections that are driving the technology forward. High performance, that's a given. Efficiency, we've got to do things more efficiently to be good stewards of the earth. A big piece of this is actually, optimizing the architectures. And we've had, domain-specific architectures for some time, but they're even becoming more profound today. Before we used to talk about just a CPU and maybe a GPU, then we added the DPU. And then when you add AI in there, you start to find out that, hey, the math between AI and HPC is a little different. And so having these highly optimized architectures are going to be critical to hit that performance and efficiency curve that we need. The software in the ecosystem's got to be easy, open to the community. Already talked about the security importance. And the thing that we're here today is the networking. The networking is becoming one of the most critical cogs to make these large-scale distributed systems work. And when we look at, AI and HPC, if you look at kind of the growth, AI is about processing data efficiently, in a way that helps humans and machines and makes better decisions. But today, there's this ever-increasing gap between that ability, the industry's ability to process and store, the amount of data being generated and processed, than what we need. I mean, if you look at these charts, the AI compute requirements are doubling about every 4 months or so, far outpacing Moore's law, arguing the case for, heterogeneous compute and domain-specific, clearly. The performance of leading supercomputers is, I say only doubling every 1.2 years. That's a pretty dang good pace, but even that's not keeping pace with the compute needs for AI. And when you look at AI, the memory growth is growing, at 20x, clips a year, since 2018. So driving these larger recommendation models and just larger models in general, are really pushing the memory subsystem. And so what this really illustrates is the great impact that AI is going to have on the future demand for data processing, storage, and networking. And, in the past, we always talked about, we used to draw this graph a little differently in the past. We used to have a general purpose CPU in the middle, and we had HPC on the right for, highly performant FP64 kind of codes. And on the right-hand side, we had, optimizations for rendering kind of products. So if we drew this again today, we'd have a third top mound. But, if you look at HPC and AI, they are driving unique but similar challenges. They are similar in scale. They're different in data formats. They're similar in needs for high performance fabrics, and yet at the same time different in terms of bandwidth and latency and congestion and so forth. AI training involves the computationally intensive process of training a model on a large data set to learn patterns and optimize its parameters. AI inference is less computational demanding in terms of its size, but it's still, tens of GPUs instead of thousands of GPUs. And so what we're learning, between the AI and HPC, as you can see, right on the left, we have FP8, FP6, FP4. Who knows what the next format's going to be? The one on the right, legacy HPC, MPI, message passing, very much, FP64, OpenMP, Fortran. So similar but different. And so what we've been working on then is, that just screams for the necessity of a heterogeneous computing. Whether we've got to have optimized compute, we've got to have these adaptive performant SoCs and FPGAs, we've got to have optimized accelerators for networking, the GPU compute, full custom, we do full custom in the market for gaming is another heterogeneous compute to think about all the way to full ASIC. And so it's really important that we enable this broad ecosystem of components to go enable that. And so at AMD, we've done a couple things. If you look at our EPYC family and look at Zen 4, I would argue that this is actually heterogeneous compute already. If you look at Genoa, it's more of a classical big core, high performant core optimization. Genoa X, we add 3D stack cache to bring a super large, more than a gigabyte of cache into technical compute. Bergamo being optimized for cloud native and understanding the data locality difference between a cloud native application and a monolithic large legacy application drives an entirely different requirement on the data locality on the cache layers. And then, the Sienna being introduced real soon is performance per watt optimized and lower power for that embedded edge telco. But they all use the same common building blocks at the bottom. We piece them together differently. And so by nature, then it's really a heterogeneous, compute optimized for the different workloads. And then when we look at the Instinct family, again, using our chiplet architecture, packaging technology, we can optimize these things differently. So we've got the MI300A that's sampling now. It's the world's first APU. So we combine Zen 4 cores with 128 gig of HBM. And what's really beneficial about the 300A is the fact that it's a true shared memory. So no longer am I passing buffers around. I'm passing pointers around between the CPU and the GPU as they're operating on data. And then we take the same architectural concepts and packaging, and we change up the packaging and we squeeze out the 300X, which is targeted at optimized for leadership generative AI. While the 300A is going to be great for HPC and great for AI, it's not as optimized as the 300X for AI. And we get that optimization because we're getting 5.2 terabytes of memory bandwidth, more HBM memory up to 192, and an incredible amount of fabric bandwidth from Infinity Fabric. But they're all based off the same CNDA3 architecture. Because of the advanced architecture and packaging, we can mix and match the 5 and the 6 nanometer processes, and all using our ROCm stack. So that's enabled AMD to really lead in the exascale era. So we built and stood up the first exascale computer with Frontier. That was based on Milan and an MI200 Instinct GPU. And that was really, if you look at those two and the way it's combined, it was the world's first discrete APU. So it was a coherent CPU, GPU, and that's enabled us to get to that #1 supercomputer, top of the Green 500, pretty much every world ranking up there. Frontier is at the forefront. It's also the #1 for in the AI world as well in terms of large scale computing. And then, that's enabled us on the next one. So we learned a lot. And what we're doing on the next one is El Capitan, which is actually using the 300A. So we're squeezing the Zen and the Instinct together into that APU. We'll get a lot more power efficiency, and we'll be doubling the performance of Frontier to more than 2 exaflops, in that time frame. Now, along the way, though, we've learned a lot, with our partners at the Department of Energy, with HPE, with Oak Ridge and Livermore. We've learned a lot about the challenges of large-scale systems, large-scale networks, how the AI starts to interplay. And so we've seen a lot of different classifications, from the front-end network to how GPU scale-out RDMA works on large-scale HPC, to how, when you take those same large-scale systems and you start to do GPU rack scale, how things start to play out on the fabric side, and how HPC is and AI are similar but different. And so, when we look at it, then, if you look at these large-scale distributed systems, whether it be an AI system on the left or a large-scale HPC on the right, the time spent in the networking is becoming, a bottleneck. On the AI front, it's a very fast-moving code base. It's got higher bandwidth constraints, generally speaking. It wants higher bandwidth than HPC. And it's a new balance of compute, network, and memory. And there's a whole new set of benchmarks. So that's a challenge for us in the industry as well. And on the HPC side, we've got decades of highly tuned codes that we don't want to break. We've got, the dynamic communication patterns are well known. MPI infrastructure is well known, and the benchmarks are also well known on that side. And so what we're trying to do is figure out, well, how do we advance this going forward? And when we step back and look at all the learnings of the past, you realize that, HPC and Ethernet, Ethernet's already, more than 50% of the interconnect in the top 500. And in fact, if you look at the top 10, especially when you look at Frontier and El Capitan, those will both be, 1 and 2 or 1 and 3 kind of systems. That isn't a family of Ethernet, being that they're all slingshot based. So Ethernet is making a big dent in the HPC space already. And it's also true that, Ethernet is the predominant, use for data center networks. It's Ethernet. One of my mentors in the industry told me a long time ago, 2 things, and maybe good for speculation now, but never bet against Ethernet and never bet against x86. I'm sure we can have a big debate on the second one, but I don't think anybody will debate that don't bet against Ethernet is a good bet to take. And so what we found from all that, though, is that we've got some grand challenges ahead. If we want to really get these AI and HPC systems to really hung and to really hum along in the future and provide the performance, the scalability, and the efficiencies that we need. So, we need to address the scale problem. We need to address the network underutilization. Ethernet is well known for having some high tail latencies we need to address. There's some congestion management problems that we need to go address, along with some fragmented telemetry schemes that are ineffective. And we've got some rigid ordering requirements. And so these are the big 6 things that, as we went through this journey of seeing AI and HPC grow, merge, see the outlook for the future, and after the learnings of building a couple of the world's largest supercomputers with our partners, that led us to go spend some time and figure out, well, how are we going to go address that, in the future? And so let me pass it off here, and I'm going to, this is my guest compadre here, Dr. Jay Metz. He's chair of the Ultra Ethernet Consortium, and he's going to give us a talk now on Ultra Ethernet and what the mission and challenges are and how everybody can get involved in Ultra Ethernet. So Jay has a prestigious background, working at Cisco in the past and Rockport. He was a professor at one point in his career. He is an AMD employee now, but is also the chair of the Ultra Ethernet Consortium. So welcome, Jay.
I want to just wait and have you continue to talk about, all the stuff that I've done, because it's a lot better than I can remember. So thank you for inviting me to be a guest speaker on the keynote. Hello, everyone. My name is Jay Metz. I'm the guy with the funny spelled name. I am the chair of the steering committee for the Ultra Ethernet Consortium, and it really is a true pleasure to be able to be gifted the opportunity to talk to you about the consortium, talk a bit about how it came into being, what the problems that we're trying to resolve, and I think Robert set it up beautifully. As we've been seeing the Ethernet world become more and more applicable to these kinds of workloads, we've been noticing that there are some natural limitations. You kind of reach the boundaries of what it was designed to do, and as a result, as a living, breathing technology, we've figured out that we need to kind of improve some of it on it. So we're going to try to address some of the issues that Robert was just talking about. So without further ado, let's go ahead and start with the next slide. Okay, so as Robert said, there's an increase in the use of Ethernet as a network for being able to handle these AI and HPC workloads, and there's a reason for this. It's an incredibly flexible technology, and it makes it really easy to push those limits, right? So it's ubiquitous, it's well understood. There's an entire cottage industry that goes along with Ethernet as an interconnect network. And so it makes a logical and natural progression into solving some of these problems. So those problems, though, are very real, right? It makes it difficult when you have a technology that is designed as a general purpose networking technology to be tuned and enhanced specifically for specific workloads like AI and HPC in order to make it more efficient. And that's what we were trying to do. So next slide, please. Well, as it turns out, this question has been bouncing around for a long time. All right. And I know that in some cases people may say, well, is it too little, too late? No, it's not too little, too late. We've got Ethernet as the top performers for HPC, and obviously it's a satisfactory technology. And I use that in quotes because it's kind of an understatement of the year here. So, obviously we have a large number of companies who are trying to figure out how to improve it. So there was a lot of discussion about this, believe it or not. Should we try to integrate this into existing standards? Well, it just so happens that there are a lot of places where the standards are made. Do we work on this independently? Do we, kind of one-to-one or, multi NDA requirement? Well, that winds up being difficult to make sure that everybody's solving the same problem in the same way. So in the end, we decided that we'd start working on these improvements and then work with the appropriate organizations as we go along in the right time and in the right place. And then we would invite anybody else who may be interested to come along and play in our little sandbox. We had to get our feet underneath us, of course, and that's what we're currently doing. So that's currently the stage of the game is where we are. It's a still relatively new organization, even though the experience levels inside the organization go back decades. So we can continue the next one, please. Well, as you can imagine, we don't want to rewrite the Ethernet protocol. That would be really silly. Just about as silly as buying a new car just because the paint fades, when you're driving really, really fast. So what we want to do is we want to take a really good technology and look at it from a workload perspective. So what that means is that normally when we start to think about the protocol and the networking stack, we create the interconnect. We figure out how these different pieces fit together technologically and from the puzzle of making these different layers work together. We take that and we kind of turn it on its side a little bit, and we start looking at it from the workloads perspective, which means what are the places in the stack that we can improve and make it more efficient? And that starts at the physical layer, which is probably one of the more interesting places where people talk about the speeds and feeds all the time, right? Oh, we got 800, we have a terabit, we've got 1.6, and the Lord knows where we're going to be in 10 years. But yeah, sure, that's the most obvious advances that we're having for Ethernet, but it's obviously also not the only one. So we go from the physical layer, go up through the upper layers, and we have to handle all of these different fast requirements. All of those things that Robert showed in one of the previous slides about the 6 different items, they all have impacts at each and every layer. And so this is a holistic approach, it's a systematic approach that doesn't want to rewrite the entire thing, but it does wind up being tuned for the appropriate workloads, right? Use the right tool for the right job. And that's why we're working on different profiles, an AI profile and an HPC profile, because as he showed in that diagram of the bell curves, they're similar and they have overlap, but they're not exactly 100% the same. So being able to understand the balance that has to be struck is a key philosophical point that we take in Ultra Ethernet. So next slide, please. All right. So as I said, when you change the perspective a little and you shift from that connectivity requirement to the workload requirement, you start to see that there are a lot of touch points along the way, all the way up and down the networking stack. So I mean, we talk about the speeds and feeds, and let's face it, they're sexy. So once they start going into the stratosphere, though, you have to start realizing that there are ripple effects that we have to take into consideration. So it'll make you drool if you're a physical layer geek. But I have to confess, when it comes to the physical layer, the math goes right over my head, goes off the charts very quickly. But I can appreciate the work that goes into it because the level of precision that we're talking about is truly awe-inspiring. What you do with those speeds, though, that's equally as interesting. Now, how do you know you're going to be able to do what you say you're going to do when it comes to having a stable, reliable network with 7-figure endpoints? Well, you work your way backwards. That's how you do it. You have to start off with what you need at a very large network with extremely tight tolerances, and you have to be able to understand what are the implications there at each and every layer, right? one of the things that's very important is you have to have great telemetry. You have to know what's going on and be able to respond to what's going on inside of the network. You have to be able to detect issues inside of the network, which include congestion issues end to end. You have to be able to communicate those issues across the network so that the intelligence of the endpoints and the individual switches can make the appropriate adjustments. You have to keep it secure. You have to be able to ensure that the proper data structures and the APIs are going to be supported so that the workloads themselves at the high level don't have to be rewritten. And you need to be able to have the robust transport semantics that work with all of the above. So let's take a little bit closer look at what this all means. The next slide, please. So obviously, I didn't even realize this was a build slide. We can go ahead and build this out. Thank you. So what we're looking to do is accomplish all of these things right from the word go. It's an incredibly ambitious endeavor. And yes, it's not going to happen overnight. But the way that we've developed these initiatives is that as we start to create the maturity and the confidence and the interoperability for these different things, we will be able to have a rollout which allows us to be able to implement certain functions and features of Ultra Ethernet into existing networks in some cases, and new networks, greenfield environments in the future when it comes to physical silicon spinning and that kind of thing. Excuse me. But ultimately, again, we're going to start off with a philosophical question. What does the reliable, stable, consistent, predictable system look like with 1 million nodes? And what do you need in order to make it all work? Well, the answer is a lot more involved and a lot more complex than just trying to figure out a one-size-fits-all quick fix. And that's the reason why it was very difficult to say, hey, we're just going to tweak, we're just going to tweak the packet sizes, or we're just going to, do something like, a super jumbo frame or something along those can help, in certain circumstances, but they can also cause problems in other areas. So we didn't want to kick the can down the road. So we're examining all the pieces of the puzzle, and let's take a look of each of these in turn. And let's go ahead and do the next slide. Cool, thank you. And again, we have another build slide. All right, this is what happens when you actually don't run the slides through in your practice sessions. You just sort of look at the development. All right, so one of the things that we noticed is that the current methods for providing high performance networking, like everything else, comes with trade-offs. No big surprise there. But what we do now, unfortunately, is not the most efficient use of the network. Now, let me explain a little bit why that is. The reason is because in a network that has these kinds of involvement with remote DMA, for instance, RDMA, the penalty that you pay for things going wrong is quite severe. Now, what that means is that if you lose a packet or if you have a problem, you have what's called a go back N problem, which means you have to go back a series of packets or go back a series of sequences to be able to catch up to where you need to go and then restart the whole thing again. What that means from a networking perspective is that you essentially create a single path for each flow. Right. And that means that the entire network isn't really being maximally utilized for the ability to run multiple flows and what we call spray the packets or packet spraying across the entire network, which would be more efficient. Okay, so we want to make things more efficient. Great. What does that mean? Well, if you want to do that, you have to make sure that you can reassemble or reorder things. So you need to have flexible ordering. So the flexible ordering allows us to eliminate the need to have these rigid, connection points between each endpoint. Okay, so you want to have flexible ordering. That's really, really cool. That helps us with the application requirements because certain applications will respond very, very well to that. What else does it do for us? Well, it helps us reduce tail latency. In HPC and AI workloads that happen to get spread over multiple nodes, the results that come back are always dependent upon the last bit back. That tail latency, that percentile for the tail latency is a huge, huge problem. And so it is, as these networks get really large, it becomes an even bigger problem. So one of the limitations we found in these large networks, especially at scale, is that the tail latencies will naturally get longer if you continue to use single purpose flow multipathing. So we want to have a better efficiency across the networks. So by being able to do that, you have additional benefits as well. For one, you have highly unpredictable and fluctuating conditions in large scale networks. It's the large numbers problem. So without getting too involved into complex adaptive systems, essentially what will wind up happening is with an asynchronous method of being able to communicate with different endpoints, you wind up getting hotspots in the network. And those hotspots require much more localized and intentional remediation, but that requires better telemetry. So let's go to the next slide and we talk a little bit more about that. Thank you. So I talked, the fluctuating conditions are really where the problems can stack up, no pun intended. So what we want to do is we want to try to see, all right, how are we solving network problems right now? Well, network problems, network designs are usually over-designed. And they're designed as a result of the fact that these kinds of conditions have to be accommodated, not just for the failover situations or the load balancing situations, but because of the fact that these kinds of congestion and congestion spreading problems are very real and they're costly. So we tend to over-design our networks as a result of that, in order to accommodate that. So when you have certain types of workloads, some nodes will send and some nodes will receive at different rates. And when that happens, you can lead to the asynchronous usage of the network links. That creates incast problems. Incast is where you have multiple input coming into a single node all at the same time, which causes a backoff problem with the congestion and then a retry again. And there's multiple ways of trying to solve that problem that are currently in play, but they each come with their own trade-offs alone. So as well. So we have to make sure that when we have these kinds of situations, we have better responsiveness. And that means being able to have more intelligence in the receiver and as well in the sender. And we also have to have the ability to receive and send the proper signals and understand what those signals mean. All of that has to make sure that, the entire system works holistically to be able to solve that particular congestion problem and be able to update and make the entire network aware so that everybody knows what role they're playing. Obviously, as you can see, this is not a non-trivial issue, and what that means is that you have to be able to handle different types of semantics at the transport layer. You have to make sure that the APIs that are happening above the transport layer are able to accommodate these things. Underneath on the individual link layers, you want to make sure that the signaling is done correctly and you have the appropriate configuration that is handled right from the word go. You want to try to minimize any kind of convergence problems on the network over time. So all of that has to be secure, right? So what we're trying to do at the very beginning is we're asking ourselves along the way, what is the security impact of all of these different things each and every step along the way? Even as ambitious as this all is, we can't do everything all at once. This is one of those things that we are trying to properly address the coarse-grained solutions at the same time, with a full understanding and acknowledgement that we still have questions that are going to be answered. And I know that there are a lot of companies and individuals who are looking to help solve that problem when they join UEC, to solve the storage problems, the management problems, and the compliance and the testing problems, and the configuration issues. There's a whole bunch of work that still needs to be done. And so there's absolutely nothing is so far along that it can't add in the wisdom of others to help us join. So all of these different things are designed to help solve those 6 problems that Robert was talking about beforehand, because as we start to go forward, we know that this is not the end point, right? All of these technologies are going to be pulled apart and put back together like a Hilbert sphere, so that we're going to have additional problems in the future, and we're trying to make it as future-proof as we possibly can for as long as we can, without necessarily having to rip the rug out of the comfort zones that people currently are at the workload level. That's the reason why we're doing this in the first place. So by being able to do that, make it secure, make it manageable, make it kind of plug and play is sort of an overused phrase, but make the network itself aware of itself to be able to handle these kinds of issues that come up in these very large scale environments. It means you wind up with a less hands-on approach to solving the problems while still using the entire network. That reduces cost, increases the performance, and it increases the longevity of the applicability of the network itself. Plus, because of the fact that it's Ethernet, it makes it a lot easier to learn about, to become educated about, to have a cottage industry for support, for administration. There's a lot of reasons why we're taking this particular approach for a lot of the advantages. What are the costs and the trade-off? Well, the cost and the trade-off is that it's ambitious. There's a lot of work that has to go on, and everybody's got an opinion as to how to do that. And probably those of you on the call are amongst them as well, which is something we encourage. We encourage that kind of enthusiasm because the only dead technology is the one that's not being developed. And this one is certainly being developed. So I wanted to thank you very much. If you go to the next slide real quick, I wanted to point out that a lot of the stuff that I talked about today goes into much greater detail in a very well-written white paper that's on the Ultra Ethernet website. So all the stuff that time doesn't allow me to go through each and every one of these different items in great detail, but the white paper does. And I highly encourage you to go there and kind of fact check me as much as you can against the white paper. I hope I did a respectable job there. But I also wanted to encourage you that the website is also where we are collecting information that goes along with those who may be interested in joining the Ultra Ethernet Consortium. We're going to be using that contact form as the basis for sending up newsletters for people who want to find out more information. We are rapidly coming close to the ability to open up for membership, new members in a couple of months. So I highly recommend that if you are interested, even if you just want to find out what's going on, that to go ahead and sign up, and we'll be establishing better communication over the next few months about what's going to be happening in the future. So thank you very much. And thank you, Robert, for allowing me the opportunity to talk about Ultra Ethernet.
All righty, great, Jay. Thanks for joining, and really appreciate the great presentation on Ultra Ethernet. So kind of then trying to wrap this up a little bit, and we'll have some time for Q&A. Wanted to give you then, kind of the AMD perspective on Ultra Ethernet. And, I couldn't sum it up any better than Mark Papermaster, our EVP and CTO at AMD. We're really proud to be a founding member and contributor to UEC. We believe, it's a natural progression for our core products. We've always been involved in the open industry and feel that the open community is the best way to accelerate technology and to accelerate adoption. We've been driving that with our open ROCm stack, with our open, with standards-based products, in both the EPYC and our Pensando DPU portfolio. And we know looking forward, as I said, the world is moving more and more towards heterogeneous compute, and we need this highly tuned network to connect them all together. And so we're certainly proud to be founding member of the Ultra Ethernet group to get this thing started. And, so looking forward then, what we're really focused on in the Ultra Ethernet with AMD is trying to make sure that we hit all the goals, right? No performance collapses. We've got to be able to build these large-scale networks, these large-scale distributed systems that just work. We need to get to the end result. The journey needs to be easier to get to the end result. And we know, given the state of the world and everything around, how important security and reliability is, especially in these large-scale systems. Failures happen. It's how we deal with them, how we deal with the security is very pertinent to being able to build and get usable, reliable results. And we've got to work within the frameworks that exist. We've got to make these things work within the AI frameworks that exist and the long history of HPC frameworks, around these large distributed systems. And we've got to be able to optimize those network operations and support for these heterogeneous accelerators that are going to continue to come. Don't know what the next big one's going to be, but I can guarantee you there will be more heterogeneous accelerators over the horizon as we find new and more efficient ways to do compute. And so for us, it's, solving that. We've got to get that, advanced congestion control, that zero trust, and that openness has got to be a cornerstone to building this next generation network for these large scale distributed systems for AI and HPC. And so I want to thank everybody for joining today and letting AMD, and thank Jay from the Ultra Ethernet Consortium for joining. And I think at this stage, we'd be happy to take some open Q&A.
Hey, Jay, Robert, thank you very much for excellent keynote, a lot of good information. We have a couple of questions coming up in Slack. I can read out to help you guys. so you don't have to chase the window. The first question is coming from Tyler. What are the timelines for when you think you will start seeing Ultra Ethernet in products?
Excellent question. So I'm glad that's the first question. So as we start to move through the development in the Ultra Ethernet Consortium, we've been trying to find that sweet spot of the ability to develop and yet still have enough room for people to come in and make contributions as well. We also know that spinning silicon is a multi-year effort, so you're not going to find an awful lot of hardware that's going to be Ultra Ethernet compliant immediately. That's going to happen over time. What we anticipate is that certain companies are going to be having Ultra Ethernet ready technology that they're probably going to be putting out. We anticipate probably sometime, especially in the upper layers of the stack, to be available in certain products and features probably as early as next year.
Thank you for answering this. There is a follow-up question. If there is a roadmap where people can find for Ultra Ethernet, something online, and where they can learn about rollout of the technology.
And that is a fair question. We are actually in the process of working on that currently. So the way that the organization is developed and set up is that we have a steering committee and then we have a technical advisory committee that runs the roadmap. And it's handled by members of all the different members from all the different companies, and they are effectively establishing that roadmap as we speak. And we are looking to make that announcement within around the same time, I guess you would say, as November, the events that happen in November, because of the fact that we're still doing the kind of the final fine tuning and tweaking. Thank
you. We have many more questions coming up, so you guys will be pretty busy.
If I keep going to Jay, I'm good.
Why don't you let Ultra Ethernet work be done in IEEE 802.3 standard and IEEE 802.1 standards?
And that, so as I said earlier in the presentation, we did originally think about whether or not we wanted to start making these kind of contributions inside of IEEE. There are many overlaps with IEEE. There are also many overlaps with other organizations. There are overlaps with the memory-based organizations, with the storage-based organizations, with the interconnect organizations. So SNIA, NVMe, DMTF, SFF. Those organizations all have roles to play in this, and we've realized that if we tried to push 9-member companies' will onto IEEE, that probably wasn't going to go over too well. So it was much easier for us to be able to say, hey, look, if we develop all these different technologies as a standards organization, and we work with creating alliances and arrangements and partnerships with IEEE and IETF and SNIA and so on and so forth, then we will be in a much better position to make it usable and adoptable. Because when we actually do release the specification, it's going to be completely open, freely available to download and use. We're not going to license it. There's not going to be any pricing to go along with it. So all of the stuff that we develop is going to be openly and freely available. And we cannot make that guarantee if that's going to be going through some other organization, right? So there were a number of reasons why we decided that we wanted to do that and make sure that all the different touch points were aligned so that we could work with a number of different organizations that each had something that they wanted to contribute.
Thank you. We have a few more coming up. I will start.
I will start charging.
I will start asking questions out of order to introduce some fairness in this protocol.
Is it one person asking the same question over and over and over again?
No. Robert mentioned heterogeneous accelerators. Can you please elaborate on the vision of such accelerators?
Well, I mean, the vision of heterogeneous accelerators is just really about optimizing the underlying microarchitecture for the workload or whatever algorithm you're trying to optimize. And x86 is great for general purpose processing. It does a really good job on running a lot of workloads and running them well. Now, when you get into really deep, complex algorithms, it's not as optimized as an architecture as, say, a GPU might be for, AI training. And that's okay. We need to use the right tool for the right job. Can x86 do a large scale training? Absolutely. Is it the most power efficient? No, it's not. And so, being stewards of the earth, we need to use the right tool for the right job. Same reason why we have a DPU. I mean, if you look deep inside the bowels of a DPU, yes, there are some ARM cores or some general purpose cores, generally speaking, in a DPU. But if you dive down deeper, you'll find, an instruction set optimized microarchitecture for packet processing. It's more optimized on bit manipulation. If you look deep inside the Pensando, the AMD Pensando DPU, we have a lot of these little RISC processors that have instruction sets that don't look that similar to x86, but that's because they're doing network protocol processing. And so that's what we mean by, finding the right tool for the right job. And so today the predominant three, are CPUs, GPUs, and DPUs. I've seen other large scale media kind of companies, streaming companies, do what I'll call a VPU, a video processing unit that is highly optimized for content streaming, delivers the most streams. In fact, AMD introduced the MAD 350 for such a case, for that content distribution streaming. It's really, really good for delivering lots of content. I think most people on the phone or bridge or teach Zoom here have probably heard of Netflix and Amazon Prime, and do a lot of streaming. And there's an optimized processor out there by AMD and by others that are optimized for such kinds of things. So the question is, what's going to be the next one? I don't know. I just know one's going to come up.
Thank you, Robert. The next one is question from Sion. Is one of the stronger goals and objectives of ultra interconnectics to maximize performance of collective operation for large core counts? Besides collectives, what is your take on performance optimization for one-sided and point-to-point communication operations?
Wow, we like to put in the big ticket questions, don't they? All right, so this is the collectives of the question is one of those ones that is a philosophical one for a number of the different members of the companies. So collectives and the collective libraries in particular, we are looking to support the collective libraries inside of Ultra Ethernet at the software layer. So this is one of the key things that we're focusing on doing. What that actually looks like and how that's actually going to work is still a player to be named later, but it is a key fundamental philosophical point that we're looking to try to accomplish. There are some workloads and there are some use cases which don't want to have collectives inside of the network, right? They want to basically have endpoint intelligence run that particular workload. So the question winds up being, how do you create a semantic layer that can actually handle collectives or not handle collectives inside of the network? And that's one of the questions that's currently being debated inside. But it is a need for both of those to be accommodated. Now, how that winds up happening is like I said, still in work. And unfortunately, I can only talk about so much because there's still IPR requirements that we have to consider. But both circumstances and situations are very real outcomes of what Ultra Ethernet is working on at the moment.
Thank you. We have follow-up questions, which is an interesting one. Is it possible to architect ultra interconnect framework based on fully distributed networks like blockchain?
I'm glad you're here, Jay. I'm not touching that one.
Okay, so the short answer is yes, because the question actually is asking two orthogonal pieces. Okay, so the issue here, what would the requirements of blockchain from a networking perspective could definitely take advantage of the increased performance inside of blockchain, but blockchain is a bandwidth problem. It's not a latency problem. Okay, and so you are going to in in the spirit of a rising tide lifts all boats, the workload requirements for blockchain are node dependent, and then the interconnects between those nodes. It's less important for blockchain to have the kind of tail latency reduction and congestion reduction, simply because of the fact that the nature of the workload itself isn't sensitive to those problems. Right, it's much more sensitive to the mathematical computation for being able to build the blocks rather than the network necessary to chain them together. Having said that, it is entirely possible that the validation process for being able to do that could definitely benefit from some of the advantages going on inside of Ultra Ethernet. It is a use case that has not been brought up currently inside of Ultra Ethernet, but my back of the napkin math in my head tells me that some parts of the process for blockchain verification and validation could definitely stand to benefit from it.
Thank you. The next question is a very broad one. I'm sure people have different opinions. Which fabric is suitable for both HPC and AI? A few examples listed here.
Did they not hear my presentation? I mean,
no, this more generic one. Spine and leaf, dragonfly, or so the question seems more focused on topologies.
Topologies. All right. Well, do you want me to handle that, or you want to take it, Robert?
Nope. This is your.
All right.
I mean,
So,
I'm going to give the it depends answer. So, I mean, there's a reason all these topologies exist.
Yeah.
And so it depends on what you're trying to solve.
And topologies do matter. Topologies matter a lot. All right. And so the reason why different topologies exist, for those who don't know what a dragonfly topology is, a dragonfly topology is an evolution of well, let's start a little bit smaller. Dragonfly is a little bit complicated for those who may not be familiar with it, but let's start with a torus. A torus is effectively a simple way to think of it without having a pretty picture is think of it as a mesh where all the nodes connect to all the other nodes, right? Or at the very least, have very, very few hops to go from one node to the other. Right, they're usually done in some sort of a cubist fashion where you've got rows and columns of nodes, and then you have the depth of them, and basically they loop around so that you don't have the diameter of a network that causes a greater degree of latency. They're particularly useful when you have very latency sensitive applications with almost no tolerance for tail latency. What Dragonfly allows you to do is essentially take that concept and put them into kind of a hierarchical structure so that you have, for lack of a better way of putting it, you have a family of a small cluster of nodes that then goes into a larger cluster that can go into other small clusters of nodes, and then, again, reduce the diameter of the network from one endpoint to another endpoint. And there's a probabilistic nature of the total number of hops you have to go through. But that probabilistic nature actually increases the ability for those workloads to get better performance. All right. Having said that, right now inside of Ultra Ethernet, the question of topologies is limited, but not bounded by the leaf spine CLO architectures. Right, so the CLO backplane is one of the things that we've been trying to resolve. The leaf spine architectures have been some of the things that we've been working with, but there is some question, and it hasn't yet quite been determined as to whether or not something like a torus or a dragonfly or dragonfly plus topology is going to be a first order business, right? So we're not going to preclude the nature of topological considerations, but at the moment we haven't quite gotten into topologies because that involves routing, right? And so the routing architecture is not one of the things that we have started to touch, but it is a very important one, and it is under consideration. But just simply because of the fact that we haven't gotten into the routing question, it has been sort of named a player to be named later. I hope that wasn't too esoteric as an answer.
Well, at least we did not get into six-dimensional mesh, so it's all good.
I can talk about that if you want me to. You want me to talk about 6D tori?
Next question is again about collectives from Dmitry. Are there plans to work on standardization of in-network accelerations for collective separations?
I am afraid you're going to have to repeat that question. I didn't quite hear you.
Are there plans to work on standardization of in-network accelerations for collective separations?
In-network accelerations for collective operations. It is one of those things that's under discussion. As a matter of fact, like I said before, we've got some of the members who are particularly keen on in-network optimizations for those collectives, and others who are not. So what is likely to happen, because again, we're still kind of in the starting point here. What is likely to happen is that the in-network collectives, well, I guess it all depends, right? So we are talking about in-network compute as part of the organization. So I think the short answer is yes. There's an active development going on right now about those sorts of things. As far as the interaction with the upper level libraries, that's still in the works too. So I guess now that I think about the short answer is yes. The short answer is yes. Those are currently in the works.
Okay, since I don't see any additional questions in Slack here, I will ask bonus question from myself. Robert mentions that Ethernet is one of the more prominent interconnects in top 500. It has been like this for a long time. As far as I can remember, Ethernet always was around 50% of top 500. In the same time, in the past, we had multiple other Ethernet-based solutions, standardized solutions, has been trying to address similar needs of HPC. I'm talking about IWAP, ROCI, and many others, which all of them based on Ethernet. So in your opinion, I want to hear like what you guys are doing different compared to previous efforts, how you differentiate it, what you think will make Ultra Ethernet more successful than previous efforts.
Yeah, I think this is probably a combination answer, Jay, between UEC. I mean, the industry has been trying in HPC. There are other fabric options that have been deployed, from InfiniBand to standard Ethernet to Ethernet with a twist. There's a lot of Ethernet with the twists out there. You named a couple, and Slingshot probably goes in that category as Ethernet with a twist. But what the industry needs to really accelerate is we need that open multi-vendor, initiative to really advance. It's very hard for one company, I think, to do it all and do it all well. It's very difficult for any semiconductor manufacturer to do every aspect of every compute and network well. And by driving the industry to open standards and open initiatives, we get the collective think. So we get the collective of everybody that's run across a computing problem or a networking problem, and we can piece it together and look at the whole end-to-end solution. And I think with the rise of AI, it is really just it's accelerating so fast that the best way to go forward is together. Together is better, is in my opinion. And so to me, that's the whole reason for assembling and getting this group together, is to take all the learnings of the past, share the insights, share the problems, share the solution, and advance everybody together. Is the way that we think about it from an AMD side. Jay, I don't know if you have anything to add from the UEC view.
No, I think I think that the key thing here is that it's an ecology, right? It's an ecological question, technological ecological question, right? And like any ecology, what we're doing is we're introducing new elements into that environment, and it's only stronger because of the participants in that ecology. And as we start to move forward, we're going to see there's always going to be trade-offs, right? You're going to have the speed of movement versus the robustness and the stability of it. And for those people who want to have the robustness and the stability of it, for long-term solutions, that's the kind of stuff that we're looking to do. But to Robert's point, no one company, that's the whole reason why having an ecology of it. No one company should necessarily have that kind of burden on their shoulders, to be honest. And that's the perspective we're taking, is that we're better together.
Thank you, Jay and Robert. We have probably the last question. We have just around 1 minute left. I will try to, it's a long question. I will try to simplify it. It's again related to topologies and routings. Ultra Interconnect so far mostly talks about packet spraying. The question here, how well it's going to work with global adaptive routing, which normally assumes long-lived traffic and artifacts in the network, which can shift to another path as a reaction of congestion or reaction to networking limitations. Spraying usually don't work well in conditions beyond single hop.
Well, okay, there's a lot to unpack there, and I don't know if we have the time to do it. So one of the things that, like I said before, one of the things that we haven't yet had the ability to address now is the routing question, right? So the routing question is a robust one that requires more than just an off-the-cuff answer here. I don't disagree with a lot of the assessments that the questioner is asking. Okay, what I don't have right now is a direction or an answer for how Ultra Ethernet is looking to approach that particular issue. I do know that there are minds much greater than mine who are familiar with addressing that in their own particular solutions. The question is whether or not that gets introduced into Ultra Ethernet. And to that, I don't know. But it is a key question that is kind of looming over our heads like the sword of Damocles, because there is topological considerations that will require that kind of examination. So we're not ignorant to it. We just haven't had a chance to, in our copious free time to solve the problem yet.
So I think that's a great example of, join and bring that question and help us find a solution to get into the open community collective. So
what he said.
I don't know, Jay, I don't know if maybe you can give any more specifics on when Ultra Ethernet will be open for broad-based membership.
Yeah, so we have decided that we are going to open up for applications for membership on October 2nd. We have gotten an awful lot of interest, and so we're doing our best to get everything ready for the party. But we will be making the announcement, and like I said, if you sign up on that form on the website, you will find that you will get notified when the opening is actually there. But October 2nd is the date we are aiming for.
Great, thank you.
This was the last question. Thank you very much, Robert and Jay. Attendees, you can use Slack channel to continue ask questions in the Slack. And Robert and Jay, please, if you have a chance, please take a look and answer if there is anything new come up in the channel. Thank you again.
Thanks for the time.
Right. Thank you all for the time. Enjoy the rest of the show, and look forward to seeing everybody soon at Supercompute maybe. So.
All right, fantastic. Thanks, everyone. Now, after that great keynote, we're going to move over into our platinum sponsor talk for today. Today, we're lucky to have Manav Gupta. He's an IBM, a distinguished engineer and master inventor, as well as the CTO of IBM Canada. Manav has many years of experience with cloud computing, big data analytics, AI, and blockchain. So today, he's going to talk to us about generative AI for business. If you have any questions, please just pop them in the Slack channel for our platinum sponsor talk. And Manav, please take it away.
Thank you, Ryan. Quick check. Can you guys hear me okay?
Yes, we can.
Perfect. Okay. So first of all, thank you for giving me the opportunity to spend a few minutes talking about IBM's point of view around generative AI and what we are doing with some of the largest clients in the world within that area. So look, I'm sure by now you are all experimenting and deploying foundation models or large language models in your own enterprises. I thought I could just take some time and talk about how, as we are working with some of our clients globally, we are beginning to see sort of a change and an emergence of a new AI workflow. And then I'll quickly talk about some of the research areas we're working on with regards to new large language models, and then maybe I'll give you some demos, etc. So I'm going to attempt to do all of that in the next 10 minutes. Let's see if screen sharing actually works here. Give me 30 seconds here. Okay. I'm going to try this one more time. Does it work? Excellent. Okay. All right. So just one, maybe two pictures. So what this picture is attempting to show you is on the left is what used to be our typical AI workflow. So at the very bottom, we all had within our own enterprises or perhaps from external sources, the amount of data that we were targeting. And we would all go through some kind of a data selection and curation process within part of data collection and preparation. We would then engage in data engineering and labeling, and then therefore use it for each of the individual downstream business challenges. So we would go through this elaborate process of model development and training and validation, and eventually into deployment and rolling out into production. I think we now are at this point where with the use of foundational models, that workflow then changes, that we can then take all of that target data, and if we curate it the right way and pre-process it once, we can then take that large data set and apply various self-supervised training algorithms on top to generate one or more foundation models, so that the downstream tasks can be optimized, or the same foundation model can be deployed for individual downstream tasks with a small set of labeled data. I mean, none of this is a surprise. What's interesting is from an enterprise perspective, this change in the modality of the AI workflow is giving enterprises a reason to pause and look at, are they organized the right way? Do they have the right data across the various data sources, lake houses, warehouses, etc., that they might have? And also investigate, do they have the right lineage? Can they trust the data, etc.? So purely from an enterprise lens, there is some angst that many of our clients are going through, I find. So with that backdrop, the approach that we took within IBM is we introduced a couple of months ago this new platform that we call the Watson X platform. The platform itself is comprised of three components. So there is watsonx.ai, which is a prompt tuning and model ops environment, which allows you to train, validate, and fine tune and deploy on a cloud of your choice the models. And I'll talk about the type of models, etc., that you can work on there. We are also finding that number of those clients, because of the desire to leverage and govern the enterprise data in order to seamlessly or near seamlessly train and tune those models. So watsonx.data is our data lakehouse, and then on the far right, I think, is our key expertise around being able to explain the AI workflows, provide model monitoring, bias, drift detection, etc. So that's the approach that we are taking. The question that I generally get at this point is, well, okay, what if my organization is using open source models, or we're building our own, or perhaps we're using it from any of the third party or closed source models? The approach that we are trying to take is this entire platform should provide you a capability on a cloud of your choice, ability to build either your own model or use open source models, and I hope some of the IBM models will make sense. And within that spectrum, we provide you the capability to try. So effectively do prompt tuning, zero-shot fine tuning, etc. That you might want to do. Fine tune the models, build and evaluate your applications, and deploy them on any cloud. So long as there is a open API, excuse me, support by any of the models, and then you are able to trust the supply chain of the models, you can bring those models into this platform. Let me quickly turn around, and I hope that the screen sharing will allow me to do that. So I'm going to stop my PowerPoint presentation here. So to give you a flavor of what that looks like, so here is the Watson X platform. So if you just, today it's available on IBM Cloud, soon to be available on both AWS as well as Azure. So this is what the prompt lab looks like. So if you log into that, and if I will turn on the prompt builder, I can enter my instruction here, and then I can provide some examples of zero-shot, few-shot, etc. that you might want to do. And then on the far right here is I can select any of the models that might be of interest to me. And then I can clearly do things such as change the decoding capabilities of the models, and then change some of the parameters like the top key, number of tokens, etc. So this is available at your disposal. There is a full history that you get provided here. And there's a wide range of these models, IBM, third party, as well as open source models that are available for you. Now, beyond language, the other modality that we are working on is geospatial with NASA. So we open sourced on Hugging Face the first round, I'll say, of the geospatial models. So and those models range from 100 to a 300 million parameter range. So go have a look at those, please. Another modality clearly is around code. So we started with a code assistant initially with Ansible. So here is a small snippet of a YAML file, and the way the model works is so this is my VS Code environment, and at the bottom, and I have configured my code assistant here, so you can see Wisdom being the code name for that model, and I can provide the model a prompt. So in this scenario, I'm working on a playbook to provision some resources in Azure, and when I give it a prompt, the model then gives me a recommendation for a bunch of code, and then if I like the code, I can press tab to accept it, and then the model runs in real time. So that's a very small flavor of the type of capabilities that we're working on. I really wanted to end on this page in the interest of time. So I think governance and responsible and ethical use of AI, especially in enterprises, is going to be paramount. This is an area where we think that we have quite a bit of understanding and quite a bit of, I'll say, history in it as well. So if you look at our example of an end-to-end governance process, so once the model proposal has gone through the approval process, the model entry is created in the model inventory, which effectively captures the facts about the model throughout its life cycle. The entry in if the model already exists in the inventory, it will be updated with new information. The data scientists can use the tool of their choice to develop the model. They can train training data and metrics from any of the open source frameworks can be provided. The model is then reviewed and then approved for production. So basically they can build the model. Once they're building the model inventory gets updated. We can sync the model status and metadata as part of model risk and governance. And then on an ongoing basis during inferencing time, once you have the model deployed into production, we can monitor the model for accuracy, drift, and bias. And then we can continue to do post-deployment model monitoring. So all of these capabilities that I quickly flashed through, they're all available for your use and try out today. Most of these things, if not all of these things, have an open source version of these available as well. So for example, for all of the model explainability, bias, etc., if you search for frameworks such as AI Fairness 360, AI Explainability 360, you'll find open source versions of all of those available. So with that, I'll pause and see if there are any questions. And I hope that this gave you a little bit of flavor of where enterprises are thinking about generative AI within their ecosystems.
Okay, thanks, Manav. If people have questions, feel free to put them in the Slack. I'll start us off with one. So on your governance model, this is really interesting. So when you're rebuilding those models, what do you find is the limitation for a lot of it? Is it the metadata collection? Like how frequently are you seeing clients actually rebuilding their models with the feedback that you get from the governance layers?
So I'll break that, Ryan, into two parts. So one, I'll call it sort of during the initial model development itself. So if it is a client that's starting to build a model from scratch, they may go through several iterations at that point. So that's one element of it. And the challenge that they've always had there is, can they capture all of the facts pertaining to that model throughout the model development lifecycle? So, and that might be the source data, the data that it might be, pre-trained on, how the model performed on various other benchmarks, whether it's Toxigen, etc. or truthfulness QA, and so on and so forth. And then eventually through the development process, once the model is approved and ready to go, you deploy it into production. And then as the model is behaving and it performing its tasks over a course of time, we're generally finding about a 18-month, I'll say, half-life, wherein they might want to go back and retrain the model because the reality then begins to deviate from how what the model has been trained on.
Okay, that's interesting. So how much metadata do you need to collect? Because 18 months is a fair amount of time between the models themselves, right? So I don't imagine that you're collecting metadata at very fine grain level when you're running your inferences then?
It depends upon the industry that the client is in. So especially in regulated industries where, let's say, a client in a financial services industry has to validate to the regulators that if our client was declined for a loan application, did that happen because of inherent bias based on age, gender, racial demographic, etc. So in that scenario, the mortgage loan approval or the credit loan approval, really every inference might have to be recorded in order to provide evidence of that. So in some cases, the amount of data collection can be quite large as well.
Yeah, I can understand that. I've done lots of data collection with HPC systems. Great data collection is a non-trivial problem. So I just had one last quick closing question. So you mentioned that this is available on IBM today and it's coming up on AWS tomorrow. Can you tell us, is it going to be available on any other platforms that people might be using?
So IBM Cloud today and soon to be available both on AWS as well as on Azure. So actually, I'll say correction. So it is available on AWS as well today, including IBM Cloud, and it's coming to be available on Azure later this year.
Fantastic. Thanks. That captures an awful lot of the cloud market. So I hope to have the opportunity to take a look at it. Thank you very much. That's fascinating, Manav.
Thank you. Thank you, Ryan. Appreciate it. Thank you for having me here.
Thank you. Okay. All right, everybody. You can continue the conversation on the Slack channel if anybody has any further questions. Otherwise, we're going into a quick break now before we get into our second keynote of the afternoon. So be sure to be back here at 10:30 Pacific in just 13 minutes for our next keynote. Thanks, everybody.